Hey students, welcome back. This is part 2 of 3.4, all right, our ideal gases. So what we've got going here in this example, we've got a lot of things going on. So we've got quite a few steps to do here. So we have a 12.5 liter scuba diving tank, contains a helium-oxygen mixture. We have 24.2 grams of helium and 4.32 grams of oxygen at 298. We're supposed to calculate the mole fraction, partial pressure, and then the total pressure. So like I said, we got a lot of stuff to do here and not a ton of space, so I apologize in advance. You may have to add this to like another piece of paper or something like that. So let's first start by finding our mole fraction of each substance. So what we're going to do there is we're just going to take it here. We know we have 24.2 grams of helium, and we need to get that to moles. So our first step is to divide by the molar mass of helium. So we've got 4.003 grams of helium there. This is going to tell us our moles of helium. So if we take 24.2, divide that by 4.003, and we're going to keep quite a few in our decimals here. So let's say 6.0455, just to make sure we have enough. And this is moles of helium. All right, we're going to do the same thing with our oxygen. We have 4.32 grams of O2, and we're going to take that to moles, and we're going to divide by 32.00 grams of O2, and that would be 1 mole of O2. So 4.32 divided by 32, and this one gives us 0.135 moles of O2. So to kind of jump right in and find our mole fraction of each, we can do that because mole fraction, remember, as an overall, mole fraction is like the chi of helium, and we're going to take the moles of helium over our total moles. All right? That's an O. That's an A. All right, total moles. So if we do that, we can easily find our mole fraction right here. We're going to take 6.0455. This is for helium. And we're going to take it over 6.0455 plus that 0.135. This is going to give us our mole fraction of each. So for oxygen, we're going to take 0.135 over 6.0455 plus 0.135. All right, so same thing, 6.0455, and we're going to divide that by, and this is our total, and we may want to add these up and like kind of keep it separately, because it will be something we use, but here, and again, let's keep about 4 decimals in our answer just to make sure we have enough. We're going to say 0.9782, and there's actually no label on mole fraction, so this is our mole fraction of helium. All right, we're going to do the same thing here. Forgot my parentheses. And down here we get 0.0218. And this is our mole fraction of oxygen. So this is our first part here. Now we're ready to figure out our partial pressures of each, but we got a little bit of work to do. At this point, we can now plug in, we know moles of each, and we know we can add them up, right? And that was what I was saying we should do separately. So let's go a different color. And we're going to say 6.0455, right? Because here's what we got. Our next part of this, kind of slide over a little bit. We're trying to find the total pressure of the system. So PV equals nRT, and our total pressure would equal our total moles. So we can find P. We know our volume is, I want to say 120 or 12.5. All right, then we have our moles, and this is where we can add them up. We're going to take 6.0455, and we're going to add the 0.135 moles. Then we're going to take our gas constant, 0.0821, and then we're taking our temp, 298. All right, and this is going to tell us our total pressure of the system. So P is going to be equal to, all right, and this pressure right there, 6.1805, all right, times 0.0821 times 298. And then we're going to divide that by 12.5. So our total pressure in the system, if I did this correctly, is 12.097. We'll go back and look at sig figs here. What do we need? 1, 2, 3, 1, 2, 3, 1, 2, 3. So we need 3. So we're going to say 12.1 ATMs, right? That's our total pressure of the system. Now we can use our partial pressures to figure that out, which is kind of one of the steps that, or the reason we did the steps here. So we'll go to a new color. We know our total pressure is this 12.0917 or 97, right? We also know our mole fractions of each are this and this. So if we take, for helium, to find the partial pressure of it, we can take 12.097 and multiply that by our 0.9782. This is going to give us our partial pressure due to helium. All right. And so the partial pressure due to helium is 11.8. And again, that's ATM. Awesome. And then we're going to do the same thing for oxygen, 12.097. We're going to multiply that by 0.0218. And again, keep 0.264. Boop. 64 ATM. And that gives us everything that we were looking for in that problem. All right, awesome. One last type of problem to do, and this one's a little bit easier than what we just did there. So hopefully that helps us. All right, we go on to collecting a gas over water. What happens when we collect a gas over water? Well, as we collect that gas, the gas, as it's bubbling in through the water, will take some water vapor with it. All right, it will take some water vapor. That's not a V. It will take some water vapor with it. All right, causing the pressure to be slightly higher than it should be because it now has water vapor in it and not just solely the gas we are collecting. But water is a really good one to use because it has a really, really high vapor pressure. All right, or a really low vapor pressure because of those intermolecular forces. So that's actually why we collect gases over water and not like collect them over like alcohol or rubbing alcohol or something along those lines. So let's take a little peek here. This problem says, in order to determine the rate of photosynthesis, the oxygen emitted by an aquatic plant is collected over water at a temperature of 293 K and a total pressure of 755.2 mmHg. Over a specific time period, 1.02 liters of the gas is collected, and we're trying to figure out what mass of oxygen forms. So what we've done, and this goes back to Dalton's law, right? We know that P total is going to equal P of our oxygen plus our P of our water vapor, right? And so what's going to happen is you're going to be given a table of water vapor pressures, which is something I already went out and grabbed right here for us. So we know our total pressure is 755.2. We're looking for our partial pressure of oxygen, and we know water at that temperature is 17.55. So to solve for oxygen, we just subtract each side by 17.55, right? Which will give us our partial pressure of oxygen. Okay, so we're going to take 755.2 minus 17.55. This gives us, I'm going to scroll up just a little bit, 737.65 mmHg, and that's based on our oxygen. Right? So now we need to just take that to, while we're kind of working here, we're going to convert that to ATM by dividing by 760, because that'll take us to ATM. So we're looking at 0.97 atm. And now we can plug that into PV equals nRT, find N, and then we can find moles. So let's keep rolling. So we know 0.9706 times our volume, 1.02. We're looking for N. We have a gas constant of 0.0821, and our temp is 293. All right, so solving for N. So our N, number of moles of our oxygen, is 0.04116, right? Because it was 5 and we rounded up. And this is moles of O2. So now we just need to convert that to grams. And we can do that by multiplying by the molar mass of O2, which is 32. And this will be our answer. So multiply that times 32, and we should get 1.32 grams of O2. Awesome. See you next time.